No.
The movement. What kind of movement? Aristotle movement. The Arsenval or the Weston. All right. The Michael Weston one. All right. And so the indicating needle is attached to a movable coil. And as current flows, how come I don't say as voltage flows?
Voltage doesn't flow.
Because voltage doesn't flow. As current flows through the coil, the north end of coil is repelled by the north of magnet. And attracted to the south of the magnet. The more current flows, the stronger the coil and the more the needle deflects. So the more current flows, or now, the stronger the coil, the more the needle deflects. The amount of current required to turn the needle amount of current required to turn the needle will depend on the magnet strength, number of turns in the coil. What's it that mean?
How many loops?
Yeah, how many loops? Just another way of saying loops. And if we go back and take a look at something here. Oops, there. How come the scale is like from here to here and not like from here over to here?
It doesn't work like that.
It doesn't work like that. Well, he's right, actually. It's just the way, because if you get too far, it's going to start pulling it back around. So this is the effective range, is only a certain arc. You can't make it much more than that with the way this works. All right, back to here. There you go. Only suitable for measuring DC. Why? Why can I not measure AC with something like that?
Because AC alternates current.
Okay, AC is called alternating current, which means the plus is not only the plus half the time, sometimes the plus is the minus, and so on. So what?
So the needle be going.
It would be doing it. It would vibrate back and forth. And so then you'd what? Take an average? So it would vibrate rapidly. So AC for alternating current would continuously reverse and vibrate. It would continually reverse, and really that would just result in a needle that just vibrates. So that's the D'Arsenval.
Could it get hot enough that it would get melty?
If it gets hot enough, would it?
Because it's moving so fast?
It's, well,
Not- or
it's
is
not
it
that this,
moving
it
fast?
just wouldn't read anything. You can try it. It just vibrates. It doesn't work well. All right. Let's see. Other movements. DC or AC. Something that works with DC or AC. Well, how could we devise something that would work with both of them? So as I just stated, in AC, the voltage and current reverse. So if a DC only movement is used, the needle will just vibrate. All right, so there are two types of analog movements. What does an analog mean? What is analog?
As a gauge with a needle.
It's a gauge with a needle. It's not digital. One. I don't know why it's numbered like this. Just stick with me. Usable on lower frequencies. 15 to 1,000 hertz. What in the heck does that mean? Hertz. What's another name for hertz?
Oscillations.
Yeah? Cycles per second. So Hz is equal to hertz. So Hz is hertz, which is equal to cycles, CYC, cycles per second. And what that means is, and we'll let this be like my 0 line. This is 0 volts right there. So it comes up. So every time we have something from like right here to right here, where it went all the way positive and all the way negative, that is one cycle. So between here to here is one cycle. I could also do it from like a peak here to a peak here, as long as you're picking the same thing. Now I can't do 0 here to 0 here. It's half a cycle because it went up. It didn't go back down. It go back down. So it's one cycle. And in the current in our house, it does this 60 times per second. So 1 second is going to go back and forth 60 times. So that's 60 hertz. So lower frequencies is 15 to 1,000 hertz. So that means it does that 1,000 times per second. Okay. And the thing I'm going to talk about is a dynamometer. Dynamometer. Or a dynamometer. It's made out of little pieces of dinosaur.
Sounds rare.
It's extremely rare. They're very expensive. There we go. Let's go back to this for a minute. DC only, right?
Yeah, right.
Because we're running current through here in one way, and it makes this north. If I turn it around, go the other way, it makes this up here south. So we got to figure out some way to swap ends constantly and keep one side north or swap them together. And that's what happens over here. So current comes in through here and it wraps around this way and it comes over here and wraps around there. So this is north and this is south. Let's say this is north and this is south. And the needle has to go this way. So what is this going to be to make it work? I'm going to say north because it wants to come down and match up to this. And this has to be south. And so for one cycle, that's exactly what's going to happen. Then, as it goes through the next cycle, it's going to swap. This will be the south, this will be the north, this will be the south, and that'll be the north. So when the current reverses direction, it reverses direction through the whole meter. And when it reverses direction through the whole meter, it changes the polarity of everything. So the polarities always stay in such a way that the meter will actually work. Can you see that? Yeah.
So trying to picture how it would move in direction. So if it's going north, go this way, then just turn right back around if it's going south?
Well, it changed, the magnets change because the current's changing direction. The current's changing 60 times per second. And so it's changing fast enough that it actually makes the magnets switch. And so the two average out and read where it's supposed to.
What about inside? The needle connect with a permanent magnet? Or it's... it's not...
Nope.
No.
Electromagnet. See? Electromagnet. So it's not permanent, it's electro. So because it's electro, if I turn this off, there's no magnet left. Yeah.
What would do the reading? Just
AC. It'll give you a stable AC. That's basically what is inside your Simpson.
Because it works with DC too?
Works with DC too.
Because
Because
they're both electromagnets.
if it's just DC, then DC is, well, we'll go back here. We'll
Just,
see.
it just won't change.
The DC looks like that. And so it would be the red. North would always be north, south would always be south, north would always be north. And the red would stay constant. And it would work just fine.
With an alternating current, the magnet stays in one place as the polarity is changing?
Yep. Yeah. And you can see it has a spring to hold it in place.
Yeah, I was gonna say that. So the needle's not necessarily fixed to the magnet. It has, it's. I mean, it is, but it's.
There's two magnets in here.
Free. Yeah.
There's a rotating coil magnet. These are rotating coil magnet and a fixed electromagnet.
Well, they're both electromagnets.
Yep. Didn't I say that?
No.
I'm sorry, I meant to say that. There is a coil electromagnetic here, fixed to the needle, affixed to the needle, but it is an electromagnet. And then out here, there is an electromagnet that is stationary, attached to an iron core.
So if I can just kind of ask a question, is the coil on the outside of it?
Yep.
Is going to be the opposite of the one on the inside?
Yes.
So it's just keeping it uniform.
Yeah. Yeah.
Wait, what does it read again? AC,
The inside
AC
coil
what?
changes.
80
What?
volts, AC.
What is it doing?
What does it read?
Well, we're going to talk about that, but you can use it to read amps or voltage. But in reality, think it through just a little bit. What has to happen for this to become a magnet? Current flow. So it's current flow. So this is always dependent upon what? Current flow. Is it dependent upon voltage? Not really. It's dependent upon current flow.
So the inside magnet changes polarity too?
Yes. That's why they're different colors. So when it's swinging up, like I indicated here, red, this is north, this is south, this is north, this is south. When it swings the other way, then the blue takes effect. This becomes south, and this is north, and this is south, and this is north. But you need current flow. And we're going to circle back around on that one. All right, want me to write down some, oops, it's right there, circle, okay. Let me see, what do I write? Uses an electromagnet instead. Instead of what?
Permanent.
There you go, permanent. Coil and needle. Well, coil, hang on, rephrase that. Coil, needle. Is connected. Oh, I'm already not. Let's do this here. Is this connected in series or parallel? This right here, in series or parallel? Why is it parallel?
No parallel, of course.
Yep. Would it work if we connected it in series?
No, because it'll all be flip-flopping at the same
Actually, it would work. Believe it or not, it would work. You just have, and it's the direction of winding. So if you wind it one way, it's the left-hand rule of thumb, and I'll show you guys that in a few weeks about how current flows this way, the force goes around this way, and anyway, but it would work either which way. All right, so coil needle is connected in either series or parallel. It'll work either which way. To A, we'll say A stationary electromagnet. Magnet. Indicating, indicating needle always moves in the same direction regardless of polarity. Why is that?
Because of the electromagnet.
Because why?
Of the electromagnet.
Because the electromagnets.
Because the polarity flips on the electromagnets and
Yeah, because it just flips the polarity. If you get your leads wrong, it doesn't care. It just flips everything inside the meter. It's like, hey, that's fine. Because the north, it's going to create a north and a south on one side that's going to repel each other. So we can say that is because polarity of both the needle and coil change together. All right, so another type is the iron vein. I'm going to slide this over. Is everybody cool with that?
Take it easy.
Whoa, take it easy, okay. Then how about I just pull up the PowerPoint while we wait?
Another. You go right ahead. Freeze it and then do it.
All right, you good? I mean, I had to write it. What's taking you guys so long?
You knew what you were writing.
Uh-oh, I forgot. Are you good?
Justin?
Justin's my tail end, Charlie.
I'm your pace car.
Yep. That sounds nicer, actually.
I'll second.
All right, I'll come back to this. So the next one we're going to talk about, and I'll show you a picture, is an iron vein movement. So, all right, you should be able to figure out how this works right away. Solenoid, what does that mean? What? The solenoid's electromagnet, all right, that does some sort of work. So current flows through here and creates a what? Magnetic field. And you have an iron vein. Well, guess what? Iron is attracted to magnets. So you have a spring down here. And so the more current that flows through here, the more it's going to attract this iron vein, which is going to pull in and give you an indicator. Now, I don't think I wrote this in my notes anywhere, but help me out here. Is this going to be good for AC, DC, or both?
What DC?
Why DC only?
Because it can't change polarity.
Because what?
It can't change polarity.
What can't change polarity?
Magnets.
Well, the iron vein can't change polarity.
Yes.
But if it's iron, and this is a magnet, would the magnet not attract iron no matter what?
You got me there.
Kind of did. On the surface, it really looks like it's just a one-way deal. But if you remember, we go back to something that only worked at DC. It had two magnets, and one of them was a permanent magnet. So do we have a permanent magnet here? No, we just have a piece of iron. So if you're kind of lost on that, if I got a magnet, and I took my magnet and one end, and at the north end, and I tried to stick it to my metal thermos, would it work?
Yes.
Yeah, and if I turned it around, would it work?
Yeah.
Yes.
And you're shaking your head no?
Why? It's
Sophia.
both sides.
Why not, Sophia? She didn't know. I don't care. What?
I'm listening.
No, I know you are. I was just trying to see why you disagreed. Sophia'd be right. Stainless steel. It's not magnetic. But anyway. Actually, not all stainless steel is magnetic. Some is, some isn't. Anyway. Okay, but yes, assuming it was magnetic steel, it would work both ends, north, south. They wouldn't care. So this is just going to be drawn in, whether this is the north or the south or the north. It doesn't matter. It's just going to pull it in. So it should work in both ways.
Would it be more sensitive?
So it will be working for AC, right?
That's the way I see it.
Yeah.
Wouldn't that be more sensitive in AC?
More sensitive than AC?
In AC.
In AC.
Because
The skin effect?
oscillation, yeah.
Possibly. I don't really know if it's more or less effective than to have double coils that are working together.
I thought as it oscillates, it makes a bigger magnetic field or a stronger one.
No. We'll get into that when we get next semester into magnetic fields. All kinds of stuff you got to get into. Like, oh crap, we're going to talk about that too. So we do magnetic fields, skin effect, hysteresis effect. Let's see, what did we just do? All right, so we're A, okay, A. So that's point A after iron vein. Needle is attached to an iron vein as current flows. Current flows through the solenoid. The iron vein. Is attracted and registers voltage. Is attracted and registers voltage. Well, that's kind of a funny thing that I wrote there. As current flows, the vein is attracted and registers voltage. Misprint?
No.
I think not. We're going to look at how that works. The reality is, when you're measuring voltage, you're actually measuring current, calibrated to read voltage, if you will.
Can I ask a question about the PowerPoint slide, for example?
Sure.
It seemed like it was linear on the scale. Is that for a reason?
It seemed like it was linear.
It was not.
I honestly don't know enough about the buildup of that one to be able to answer that.
I mean, like the
If you look,
increments were getting further and further.
right, but if you look at any meter, take the Simpson meter. It's not linear.
I mean,
Like especially resistance in some scales.
Yeah.
So it's kind of a commonality. I see that. ELECTRO, electromagnetic forces are countered, balanced by a spring, a coil spring. It puts it back to 0. All right, that's going to bring me to another type here called the rectifier type.
What was that?
A rectifier type.
You got the McDonald's or what?
I'm going to show you a picture of the rectifier type.
I don't know if I want to see this picture.
There we go. Rectifier type. So a rectifier is something that transforms AC into DC. All right, so up here, as a reminder, this is what AC looks like. It goes positive, then it swings negative, then positive, then negative, then positive, then negative. And we know that it will make the needle go back and forth if it was allowed to do that and not set up right. So when we have a rectifier type, what happens is, and I don't know if I should use a pen or a laser pointer, we're going to use diodes. And as you have experienced, diodes are a check valve, if you will, for electricity. And so there's a diode and it looks like that. And so it only allows electricity to flow in one way. Question, does it allow it to flow from left to right or right to left?
From left to right.
From left to right. Well, that was kind of a tricky question. Depends. If this is a positive and this is a negative, which way should current be flowing? From right to left. And would the diode be on or off right now?
Oh.
You're confusing me.
Would this diode allow electricity to flow?
From on.
Yes.
I'm going to go yes on that one. Okay, and here's kind of how I remember this. If you think about how did they whoever they are, how did they originally think electricity flowed? Conventional,
Yeah, conventional.
flowed from. The flow was from
Plus to minus.
from plus to minus. And it wasn't that long ago. I really want to say it was something like 1954 when they switched it and go, hey, wait a minute, we got this wrong. So that wasn't that long ago. I mean, I wasn't alive yet, but getting close to it, right? So if we go back to when these things were developed and we think about the diagram here, well, what did they write for us? They wrote a little arrow. It's pointing this way, didn't they?
That's pretty good.
And then they put a little negative right here. So, well, that negative goes to the negative, and the arrow shows which way it flows. Right? But then, we'll say 54, somebody decided everything worked different. And, well, it doesn't flow that way, it flows anything else. But still doesn't matter. We can go back to this and say, yes, that is on. Now, if I set it all up again, and I say that this is the negative and this is the positive, will current flow?
No.
It will not flow. All right. So knowing that, we can just come over here and say, okay, so here's my AC source. And remember, it's going to flip. So for this 1 second right here, or not 1/60th of a second, This is negative. So current flows from negative to positive. It comes up here, and it comes to here. Can it go this way?
No.
It can't go this way. Can you see that, Steve? Or do I need to go laser pointing? All right.
I can have
Well, it's so hard if you're back there. You guys don't realize it. All right, so it can't go this way. This is turned off. It comes up here. Can it go this way?
Yeah.
Yes. The negative to the negative turns it on. Comes up here. Can it go down here?
Oh, no.
No. So it's only got one choice. It's going to come through here, and it's going to go through the load this way. It's going to come back around. It's got to, well, now it's got to find its way through. Now, wait a minute. These are both the same. So why can't it just go this way?
Because negative diode's off.
Okay, well, this gets tricky because it's what is more negative than something else. So at this point, we're negative. Now we're positive. So it references this side over here. And since it had a voltage drop, it can't. It comes up through here and then back around there. Okay? 1/60th of a second later, it looks like this. And now it's got to flow this way. So now the negative comes up here. Can't go this way, so it comes up here and just finds a shortcut through there. Comes back through the diodes and it negative here and then back down and in. Simple?
No.
We'll get more into that when we talk about solid state stuff. But you have to just realize that the diodes that's setting up, the way it's set up, it only allows current to flow one way. So it's always going to flow through the same direction. So these just reverse it. Let me see, why was that difficult?
Is it perfectly smooth? Like, is it smooth output?
Yeah. Well, I think if you looked at it under oscilloscope, no, you're going to see some ripples because it is changing. Because it goes to zero.
Yeah.
It's going to go, it drops to zero, but that's not, okay. So it comes up here. I'll just draw. Okay, so it's negative right here, right?
Negative.
So remember, it comes up to here. Negative's going to turn, what is it going to turn on? Is it going to turn on this one or turn on this one or allow it to flow?
Q1.
Would it be easier if I went backwards? But it comes up here. This, in order for this to work, this has to be a positive and that has to be a negative, right? But it's not. What have I got here? I'm going backwards. I'm using electron theory, right? So can it turn on D4? It cannot. Everybody see that? Okay, because it would be this way, and it's off. If it's this way, it's off. All right? So this way is top drawing, on, right? On. Gets to here. Well, again, it's still negative. So can it go this way? Nope. So it's only got one way to go, down and through. Okay. Like I said, this is the hard part here. It gets to here, and we could look at it as, well, it's gone through here, and it comes up. It can't go this way because this is more negative. Well, I don't want to confuse you. It just comes up through, oops, stop that. Comes up through here and then down.
So it doesn't go to D2?
It does not. D2 is blocked out.
So basically you just follow the arrows.
Yes. Well, on this one, it's easy to do because the arrow's already there. We could try it positive to negative. Let me see. I'm going to go against the arrows. Well, no, I really don't because the whole point is it's flowing this way through the load. It's got to flow this way through the load. It has to keep flowing the same way through the load. If you don't go the same way through the load, what happens to the electromagnet? It reverses, and you can't have it reversing. You've always got to send the current the same way, and that's this whole reason why this rectifier circuit is set up, so that it constantly sends voltage going the same way. And you're going to see something almost just like this when you get into alternators, because inside of an alternator, it's making AC, but it's got to come out DC. So what does it do? It runs it through a circuit just like this, where it gets to a diode, and the diode says, you can't come. Another diode's like, come on, you're good. Right? And then it's going to swap around. This diode's going to go, okay, stop. It's like, traffic cop. And this one's like, come on, electrodes this way. So they keep everything going the same way, down the same way that the street's going. Okay? So we'll just go back here and say negative. Negative goes up. Can it turn this one on? Yes. Can it turn this one on?
No.
Nope. So it goes this way, down through here. And now we're coming through here. it's kind of a positive at this point. So if it's a positive at this point, I know it's kind of hard to go, wait a minute, that seems like it's going backwards through there, but it's still on the negative side coming through.
It's because the other side's busy.
So the other side's busy, if you want to look at it that way. So, all right, we'll get more into more positive, less positive later. But anyway, I want you to see that's how that circuit works. So when I say a rectifier circuit, like, oh, yeah, I got that. So that's a rectifier type. So that's solid state because it doesn't use moving parts. Uses a rectifier to send current through the meter in one direction. And the reason why that's important is because it keeps it going the same direction so the meter doesn't vibrate. AC meters read, anybody remember? Read in what? RMS. What's RMS?
Root mean square.
Root mean square. Root mean square, which is 0.707 times the peak voltage, or the peak. I'll just say the peak, not the peep. That is not at all what I wanted to write. Peak voltage, peak amps, whatever it is. All right, 3. Note that all voltage meters need current flow to register. Without current flow, you don't have a magnetic field. Without a magnetic field, you got nothing to read. Every single one of those requires some sort of magnetic flow. Even though the bridge circuit we just kind of showed, at least the one I showed you right there, just went through a load. But nevertheless, take out that load, make it a needle, and there you go. Yeah.
This may be a dumb question, but would you have voltage if there's no current flow?
Would you have voltage? No, you wouldn't. Well, wait, Nate, would you have voltage?
Because it says you need
Okay.
current flow to register voltage. So if you didn't have current flow, you wouldn't have voltage.
Well, I want to make sure that I answer that correctly. So in technically, it depends on how you're looking at it. So let's just take a battery. Big old battery. Boom, I set it down. Here's the positive and here's the negative. Right? For those of you watching at home, got a battery. And I got a positive post and a negative post. Is there voltage in this battery?
Yes.
Do I have a difference of potential?
Yes.
Okay. Now I'm not measuring it. Now if your question is, in order to measure it, do you have to have current flow?
Yes.
The answer is yes. So I take a voltmeter and I put it across here. Is there current flow?
Yes. Yes.
There will be current flow. A very small amount of current flow because the resistance of a voltmeter is very, very high. So it's going to block almost all of it, but it's going to allow just a little bit through so the needle works. So you actually do have current flow in this situation to make the voltmeter work. Not much, but just enough. So let's see. All voltage meters need current flow to register. Let's see. We'll put A. Voltage meters. Should be voltmeters. Actually read current flow. Calibrated to show volts based on Ohm's law, which is current flow is proportional to voltage. So if you get X number of volts to flow through a resistor that's built into the meter, then therefore there must be this much voltage, and it just shows you that. And it's something you have to watch for in aircraft. There are many things that aren't what they seem to be. It's a gauge that says something calibrated to read something else. Like a temperature gauge. It's not really reading temperature, a lot of them. Some of them do have a temperature bulb that are actually reading a temperature, but they'll convert it to a pressure that has a gauge that's reading pressure that's telling you temperature. Or it may be a temperature gauge that has a thermocouple, which is a dissimilar metal that creates a microvoltage that goes to a gauge that's really a voltmeter that's reading microvoltages calibrated to tell you the temperature. Or my second semester students, what did we deal with last semester in especially in fuel injection systems?
Fuel flow?
Fuel flow. Fuel flow gauge is not a fuel flow gauge at all. It's just a pressure gauge. Just a pressure gauge, but instead of saying PSI on it, it says gallons per hour. It's just all calibrated. And it all works if everything works.
Yeah, you get a clog.
But yeah, just like we learned, you get a clog in a fuel injection system and the pressure goes up.
Yeah, it reads higher than what it's actually.
So it tells you that suddenly you've got this high fuel flow when in fact you have a low fuel flow. It's just the pressure went up. So it's a lot of things are like that in aviation. So it works until it doesn't. All right. Is it time to go? I can hear by the zippers. All right. I guess you guys are out of here. So.